Let's now discuss the solution to exercise 1. We begin by reviewing the problem. The idea is to solve for the roots of the quadratic equation given by ax squared plus bx plus c equals 0, where a, b, and c are coefficients of the quadratic equation and are real numbers. The solution to the quadratic equation is given by x equals negative b plus or minus square root of b squared minus 4ac all over 2a. An incomplete MATLAB script and Python code was provided. Your task was to complete the script or code in order to make it solve for the correct roots of the quadratic equation. Our approach to solving this problem is to develop a step-by-step process in order to give us an idea on how to write our program or script. There are 4 possible cases leading to 4 solutions. Case 1 is when the coefficient a is equal to 0. This means that the denominator in the solution is 0. To solve for the actual root, we go back to the original quadratic equation and see that the solution is x equals negative c over b. The next 3 cases are when the coefficient a is not equal to 0 and involves the discriminant given by the expression inside the square root sign, that is b squared minus 4ac. Case 2 is when the discriminant is equal to 0. This immediately means that the solution is x equals negative b over 2a. Case 3 is when the discriminant is positive. This implies that there are 2 roots and both roots are real. Case 4 is when the discriminant is negative. This implies that there are also 2 roots and that both roots are complex. At this point, it is already apparent that we need a specific command or function or set of commands or functions to cover all these cases. The set of functions that we will be using are called if, elseif, else in MATLAB, or if, elif, else in Python. The differences in the syntax between MATLAB and Python are subtle. In MATLAB, it is elseif, while in Python, it is elif. The commands if and elseif in MATLAB, or if and elif in Python, are followed by an expression, typically a condition. If the condition is true, then the statements under the command are executed. The else function does not need an expression. In Python, the if, elif, else statements end with a colon after the expression. Finally, these functions in MATLAB are terminated by the end command or function, while Python does not require this. One more thing for future reference. I'll be using a green box for MATLAB codes and a blue box for Python codes. It would be instructive to describe the process with a flowchart. We begin with the question, is a equal to 0? If this is true, then x is equal to negative c over b. If it is not true, then it proceeds to the next question, which is b squared minus 4ac equal to 0? If this is true, then x is equal to negative b over 2a. If this is not true, then it proceeds to the next question, which is b squared minus 4ac greater than 0? If this is true, then x is an element of a set of real numbers. Otherwise, x is an element of a set of complex numbers. Here's how the algorithm should look like when written in MATLAB and Python. You should be able to see the correspondence between the flowchart and the MATLAB and Python scripts. Again, there are subtle differences between how these codes are written in MATLAB and Python. For example, to square a number, the caret operator is used in MATLAB, while the double asterisk operator is used in Python. Semicolons are used in MATLAB to terminate statements, but not in Python. You may omit the semicolon in MATLAB, but the software will give you warnings, and when you run your program, you will see all computed values in your console, which takes more computing time and for some programmers are annoying. In MATLAB, parentheses are used to call out the elements of the variables, while in Python, square brackets are used. Another difference worth mentioning is that the square root function in MATLAB accepts negative values and outputs a complex number. So there's no need to implement the fourth case in the flowchart. On the other hand, the square root function in the NumPy module in Python does not accept negative values. However, if you use the square root function in the CMath module in Python, it does accept negative values and outputs a complex number. To test this algorithm, as represented by the flowchart, I will need to introduce values for the coefficients a, b, and c. But I can't just introduce one set of values if I'm going to test all four cases. I need to be able to change the values of these coefficients. The variable z is therefore a matrix with 6 rows and 3 columns, or a 6 by 3 matrix. Columns 1, 2, and 3 represents the coefficients a, b, and c respectively, and each row represents 6 sets of coefficients. What I need to do is to call on the first row and assign these values to the variables a, b, and c. We can assign the variable I to represent the ith row in the matrix Z. Since there are 6 rows, we have to call each row one at a time, assign the row values to the coefficients a, b, and c, and then perform the algorithm for solving the roots. So we will need to iterate from row number 1 to row number 6. In the flowchart, I can simply add the question, is I less than 7 for MATLAB, or is I less than 6 for Python? If this is true, the program should just feed the elements of the ith row to the coefficients a, b, and c. You can also use I is less than or equal to 6 for MATLAB, or I is less than or equal to 5 for Python, and the result will be the same. If it isn't true, then it ends the program. It would seem that this is another use for the if command, but it's not, because the if command does not tell the program to go back to the beginning of the algorithm. In the next slide, I'll show you how this is correctly implemented in MATLAB and Python. Here's how the flowchart we drew should be implemented with the if command. I've encircled the new lines of statements related to the if command. In MATLAB, the index of a matrix is always an integer and can only be positive integers. 0 cannot be an index. In Python, the index of a matrix can be 0 and all positive integers. Thus, the initial value of the index I is 1 in MATLAB and 0 in Python. This initial value needs to be clearly defined in the program so that it knows which number the index I should begin. You should also be able to understand why I used I is less than 7 or in MATLAB and I is less than 6 in Python. The statement I equals I plus 1 means that the program should add 1 to the current value of I before going to the next statement. In Python, you can also write I plus equals 1 instead of I equals I plus 1. When you run this, you'll find that this does not work at all after the line I equals I plus 1. This is because there's no way for the program to know that it should go back to the beginning of the algorithm. What you will need to do then is to copy the algorithm 5 more times, which is tedious and extremely inefficient. The correct way to do this is either to use the while or for loop commands. Here's how it should be done when the while command is used. The only change I did was to replace the if function with the while function. With this function, the program knows that it should continue running or executing the algorithm found between the while and end functions in MATLAB, or the algorithm that is indented under the while function in Python, until the condition stated in the expression is fulfilled. Here's how it should be done when the for command is used. What are the changes? First, the I equals I plus 1 statement has been removed. With the for loop command, the program already knows to increase the value of the index I by 1, and there is no longer any need for this statement. Second, the initial value of the index has been incorporated in the for loop command. This is quite obvious in MATLAB, as you can clearly see in the expression I equals 1 colon size z1, that the initial value is 1. It's not so obvious in Python, but I'll get to that in a couple of minutes. Let me just explain the final value of the index I in the for loop, which is size z1. If you go to MATLAB's command window and type size z, this is what you will get. The variable ans has two values, 6 and 3. This means that the function size returns the matrix dimension of the variable z, which is 6 by 3. The variable ans itself is a 1 by 2 matrix, or a 1-row, 2-column matrix. So if you type size z1, it will give you 6, and if you type size z2, it will give you 3. Since I need the for loop to terminate after 6 loops or iterations, then I type in size z1. Thus, the for loop begins at I equals 1 and ends at I equals size z1, or I equals 6. So why not just type in 6 if I already know that the variable z is a 6 by 3 matrix? Well, what if later on we decide to increase the number of elements in the variable z? Should we then count the number of rows again? Putting in size z1 makes us no longer think of the dimensions of the variable z, no matter how many times we add or subtract rows to it. Now let's go to Python. In Python, we use the function range. This function returns a sequence of numbers. The initial value is 0 by default. The increment or step size is 1 by default. The final value is what you write as the argument, that is, between the parentheses. So if you type range 4, Python will give you 4 numbers beginning with 0 and ending at 3. The number 4 is not included. It just means that there are 4 numbers starting from 0. Now let's discuss the function size. If you type np, that's size z, in the Python console, you will get the number 18. That's because it will return, or it returns, the number of elements of the matrix or variable c. If you type np.size z0, it will return 6. If you type np.size z1, it will return 3. This is almost the same as in MATLAB, except in Python, the lowest index can be 0. So what is essentially written in the for loop command is range 6, and the index I begins from 0 and ends at 5. We can now see how both the while and for loop commands can be useful for iterative operations, or for operations that require you to repeat a set of commands while changing some value at each iteration. In this discussion, what we've done here is to break the problem down and describe the thought process that goes into developing a program. We provided clear instructions at each step and describe what each step does. For users with some experience in programming, this is elementary. For others who have no experience at all in programming, this step-by-step process may be quite useful. We believe that in this tutorial, we have already provided you with the fundamentals and what you need to begin developing your own program. In your first machine problem, the instructions on what to do will be given. We will provide you with skeleton code. However, no other hints or clues will be provided in the code. In succeeding exercises, both instructions and hints will be given to help you in understanding the topic, and a skeleton code will also be provided. In succeeding machine problems, however, only the instructions will be given. You will then need to make your own programs from scratch. During discussions of solutions to the exercises, the focus will be on the computational technique and not in the programming. It is now your responsibility to learn the necessary commands and functions in order to accomplish the assigned tasks. If you have any questions and concerns, please feel free to drop in during consultation hours or send me a message via email.